Then theory behind bifurcation. Um, Bifurcation is just a transition step. For example, we're looking at this problem here where we can write f now as a function. This is an autonomous system, but it's now dependent on some parameter, mu in this case. So you will then find that without mu, the system behaves like dx dt is equal to x into x minus 1. And then to find the equilibrium point, just then find that x is equal to 0, x is equal to 1 at the equilibrium points. Right? So to determine their stability, we then find this derivative of f here. Remember, this is f of x. So we now want the derivative of f with respect to x, which is just 2x minus 1. So we want now to find the stability of these two equilibrium points. It was minus 1, which is less than 0. So x is equal to 0 is stable. And then we can then do the same for the other equilibrium. X is equals to 1. This is 2 minus 1, which is equals to 1. So x is equals to 1 is unstable. So we have this original system that does not depend on any parameter u. And then we can now see that it's straightforward that x is equal to 0 is stable, x is equal to 1 is unstable. If it was an equation, the modeling populations were just going to say x equal to 0 is the extinction equilibrium. So no matter what, the system ends up settling at x is equal to 0, but it won't settle at x is equal to 1. All right, so there we are. We have this system. Now we have modified the system. Now we now have dx dt. Now I put x into x minus 1 plus some parameter. So the effect of this parameter is just pretending the system. It's making some introducing some disturbance. So we want to check how does this modify also the equilibrium point that we found. And this is now a function of two variables of x and the parameter mu. So when we find the equilibrium point, in this case, we just say x is equal to 0. In other words, x squared minus x plus u is equal to 0. So if you use the quadratic formula, you then find that x is equal to 1 plus or minus the square root of 1 minus 4 mu all over 2. So we have two equilibrium points here. X1 is equal to 1 plus the square root of 1 minus 4 mu over 2. And x2 is equal to half plus minus, half times the square root of 1 minus 4 mu. Now, but we are interested in real valued solution. So whenever we deal with square roots, for us to get real value solutions, we need to make sure that 1 minus 4 mu is greater than 0. But we can also have 1 minus 4 mu is greater than or equal to 0. Now, if we put the equality 1 minus 4 mu equal to 0, then it means x1 is equal to x2. These two, they meet. But we are interested in distinct equilibrium also. So we have to consider both cases where we have two distinct and where we have one. All right. You will see it unfolding at some point. So this is an important condition. And what we do to it is to then say, what does it tell us about mu? It then implies that so this is an important condition not to be left. For x1 and x2 to exist as distinct. So what that means is you can uh, is so don't want. So in all your analysis, be careful on what conditions you pose on you. The key condition is this one. All right. Now, given that we have two now, x1 and x2, we need to then have a check for their stability. Now, we still have to find the derivative of f with respect to x. But now, because f is a function of two variables, x and u, then we now have to use the what? The partial derivatives. But you will still get 2x plus 1 because you're not differentiating with respect to mu. So now we want to then establish the stability. So now is evaluating x1, this partial derivative, and this will be 2 into half, that's half, and the square root of 1 minus 4 mu. It's minus 1, provided u is less than 1 over 4, as usual. Right. So if we are to simplify this will be 1 plus the square root of 1 minus 4 mu minus 1, provided that mu is less than 1 over 4. I just carry this around because I want it to remind me that I should take into consideration that those conditions. So I can then now see that this is just 1 minus 4. But remember, mu is less than 1 over 4, which means this square root is actually greater than 0. Since 4. Right. So what does this mean? So it says x1 is unstable since is less than. Now, we can also say this case, we are going to say x1 is an hyperbola. Well, with some analysis at 1/4 because it still gives us, in other words, here there's only, by non-hyperbolic, it means it does not have um, zero real parts. It does not have zero real parts. Okay. So, or in other words, the first derivative here is zero. So let's do it for uh, x2. So we are now evaluating at x2. But x, this is now half or 2. So 2 into half minus half root 1, provided it's 4. So this is 1 minus the square root of 1 4 cubed minus 1, or there should be minus 1 there, which is minus 1 plus 4. Because this is less than 0, since this one is already greater than 0, 1 u is greater than 4. So then x2 is stable or locally asymptotically stable when you also need to make the same, I should say when here. And also x2 is non-hyperbolic when equals 1. So is equals to x2. Okay. So you can see that when u is equals to 1/4, x1 and x2 coalesce or they meet, they become one at least. But when mu is less than 1/4, x1 is unstable, and when mu is less than 1/4, x2 is stable. So which means this therefore means this is exchange or stability between x1 and x2 when you so whenever there's an exchange, it means that now want to now check what is the value of x1 and x2 when mu is equals to 1/4. X1 is equal to 1/2 plus half square root of 1 minus 4 1/4. So how we start value also. Right. So our bifurcation point, the not side 7 not x naught is then equal to uh, 1 over 3. So we have a bifurcation point. So this is the point where there is exterior stability. Now, what it means is we now have equilibrium points as functions of x. So you can see x1 is equals to, as a function of mu, sorry, or mu. Is now halting. Okay, so basically we are saying that we need to plot uh, this, need to plot this curve x1 and the x and mu on the x mu plane, x mu plane, where mu is the independent variable. So we would then now need to know what happens. It's just your curve sketching techniques are needed now. So for example, you then find that if mu, this is 1 over 4, so you just make some sort of a test. So if mu is 1 over 4, so this is mu, mu and x1, just to have a little bit of an idea of how this look like. Maybe we'll put x2 there, when we can easily write x2 here. We just want to have an idea of how to plot this. So if mu is 1 over 4, let me just pick mu is 0 there and it's -1, something like that. We know if mu is 1 over 4, x1 and x2 are all at half. But if mu is 0 for x1, for x1 it will be half plus half, because if this is 0, this whole thing goes to 0, so it will be square root of 1. So half plus half is 1, and half for x2, half minus half, this is at 0. If mu is -1, then you have the square root of uh, 1 minus 4 times -1, that is 5. So that will be half plus half root 5. So it is it's greater than 1, this one. So it is on top, it's just greater than 0. So for x2, it is half minus half root 5. So this is less than 0. So, and then you know the behavior of the square root function will be like this, or it will be like this, facing this direction, like that, or facing that other direction. So in this case, we can then now go to the x mu, and plot all these two equilibrium as functions of mu. So we know mu is 1 over 4. That's our point of concern. And when mu is 1 over 4, you know that x1 and x2, they are equal to half. So what we saw is the u at at mu is equal to 0. All of them, but this one is going to go through x1 is going to go through the point x is equal to 1. So it will be folding backwards, uh, but passing through the point x is equal to 1. And if u is if the x2 is the one that goes through 0 and folds backwards. So this will be your x1. This is your x2 equilibrium. And this is the point 1 over 4 half, and we call this point the bifurcation point. So the point of exchange of stability between x1 and x2. But let's look at this. x1 is unstable. So we will represent stability with a bold curve, and instability we represent it with dashed lines. So what we are going to do is to then represent this unstable equilibrium using the dotted lines. So we now have what is the bifurcation point. So now we want to establish the flow of I'm going to start here so that I can have the bifurcation diagram by itself. Right, so we then now want to then see wherever they are our equilibrium points. In this case, they're on the left-hand side of mu because 1 over 4. Just draw a straight line. So we know what happens when you when the equilibrium point is unstable. It repels trajectories. So if we start our solutions above this x1 equilibrium point, they're going to move away from it. If we start below, they're also going to move away from it. So what it means is a stable equilibrium point has to attract it. And if we start equilibrium points on this side here, they are all going to be going to the stable equilibrium point. So this is now how we show the direction of movement of trajectories on the bifurcation diagram. And here we are, we have a bifurcation diagram which shows a fold bifurcation. So you can see that we have labeled the axes, both x and mu, we have labeled them. We have labeled the bifurcation point, right? We have drawn the bifurcation curves, right? And with the curves, we have shown the one that are unstable, then the one that is stable. By unstable dashed, stable dashed. And then we have also shown the direction of trajectories. Right, so basically that's what a complete bifurcation diagram should look like. If you List n of these, then start subtracting marks. So this is an example of a saddle or a fold bifurcation. So with all the important points, we also need important points. So important points require the bifurcation point, but also the points where, if possible, the graph intersects the y-axis, the y-intercept, the x-intercept. So we need all those important points to appear. So that's it about bifurcation. Thank you.